Bismillahirrahmanirrahim. Bismillahirrahmanirrahim. This is Hafiz Muzammil Rahman. Today we are talking about the MD simulation. That is very important task in molecular modeling. And those who don't have a high specific computational resources, now there is no need to worry about it. And we should be thankful to Google Colab. By using the Google Colab, we can analyze or we can perform MD simulation by using the GPU that is provided by the Google Colab. So first of all, you will have to make account on the Google Drive, and then you will have to type this on the Google Colab, and accordingly you will have to open this the first tab, and such file or such web page will be open, and the total detail of the Google Colab, how it works and how you can use it, all the things are available on this page. So first of all, you will have to save the file, or you will have to change something, you will have to give the name. The name of this file is Muzammil MD2 simulation, and then you will have to go to the edit, and then you will have to click the notebook setting. By notebook setting, you will have to choose the GPU, and then you will have to save it. So in this way you will be connected to the GPU, and the first thing you will have to mount the drive, the Google Drive, by giving this command. When you will open it, if you will click over here file, and you will click the new notebook, so such type of page will be open, and accordingly you will have to change the name, and then these things will be empty. I have already done some work for you, because we are going to do MD simulation on the Gromacs. So by using the Google Colab, by using the system or the specification of the Colab, we will have to install the Gromacs and CMake and other tools on the Colab as well. So therefore it takes some time. Therefore I have already done or install these things for you as well. So first of all, you will have to give this command from Google Colab import drive. You will have to mount the drive, the Google Drive. This is your Google Drive, and it has been mounted. When you will give this command and you will run this, so your drive will be mounted, and then you will have to give this command bash LSCPU NVIDIA SMI. So the system which has been provided by the Google Colab, you will know the information about the system. Like in my system, I have two CPUs available, and the this GPU card, that is Tesla K80. This card is available. Okay, so then we will have to download the CMake first for running the MD simulation in Gromacs. So by giving the command bash, this is the web address of the GitHub, like this. The CMake is available here, so you can click over here and you can give the address by the command vget. So these are the Linux command. You will have to give this address by the vget, and then you will have to tar the zip file. So accordingly it will proceed like this, and you will see on your screen these type of information, and then you will have to give the command, and you will have to make the directory build in the CMake, and then you will have to run the make command, and then you will have to install make as well. So it will also take some time. These are the just command to install these libraries on the Google Colab. This is a very simple tutorial. If you want to know about the installation, you can go to the Google and you can find out how we will be able to install Gromacs for GPU. So this is the procedure of installing the Gromacs on GPU. It is already available on the internet, so you can get the command from anywhere, but I will upload the file accordingly in the description as well, or I will upload it on the GitHub as well. So you can download this specific file with the command as well. So after this, when you will install the CMake and make install, and such type of information will be available on the left side. So these folder will be appear over here. When you will start your work, so it will be like that. There will be nothing like this, and when you will run the or you will install the CMake or make install or other things or Gromacs, so the folder will be added accordingly on the left hand side as well. So after this, now we have installed make and CMake, etc, etc. So after this, we will have to install the Gromacs. We will have to download and install the Gromacs accordingly. So this is the file which we will, pardon me please. Okay, yes. So this is the file. We will go to the download of the Google, and then we will copy this address, and by giving the wget command, which we use in the Linux, so we will download the Gromacs as I am working on 2021 Gromacs. So I have downloaded this one. So this is the address for downloading the Gromacs. So whatever you want to download, so you can give the address accordingly by giving the wget command. Then you will have to start the Gromacs the folder. Then you will have to make the cd content and Gromacs, and then you will have to make directory build, and in the build you will have to give this command. You will have to run the CMake command and gmx build on fft on and etc. This is the command to install the Gromacs on the GPU. I'm repeatedly saying it. If this tutorial is not specifically installing the Gromacs on the GPUs, this is about how you will be able to run or simulation on the GPUs by using the Google Colab. But by these commands, you can also, if you have a GPU and you do not know about the installation of the Gromacs on GPU, so you can also use these commands. But these commands are specifically for installation. So after when we will run this, it will be installed like that. Or after installation, we will check whether that is installed or not correctly or not. So by giving the bash command, we're going to give the command source, after the installation source user local Gromacs bin gmrxc. This command will be given. Then it will show whether it is correctly installed or not. So these are the information. GMX is giving this information, these options, and when you will run any Gromacs command, and in the end it will give some code to you. It means all things are perfectly working. Okay, so this is till now we have installed the Gromacs. What we have done so far, we have just typed the Google Colab on the Google, and then we have opened this page and click on the file and open new notebook, and such page will be open, and here you will have to change the name, and then you will have to give the command this by clicking the code. You will have to give the command from Google Colab import drive. You will have to drive. You will have to mount your Google Drive, and accordingly you will follow these instruction. You will have to download, and you will have to get the CMake, and then you will have to install the CMake, and then make install, and then accordingly you will have to download the Gromacs, and then you will have to install the Gromacs on GPU as well. So after this, you will check whether this is installed or not. Now we are going to follow the tutorial which is available on the Gromacs tutorial page. So we have export this. So first of all, if we we are going to we are using the same strategy which has been given by the tutorial, the official tutorial of the Gromacs, so that you can repeat it very easily. So in today's tutorial, we are going to follow the lysozyme tutorial, and the protein that will be used, that will be 1AKI.PDB, but you can use any of the protein. So first of all, we will have to download the protein by giving this address. So accordingly, if you want any other PDB, you will have to change this ID. Only change this ID. Nothing has to be changed more. You will have to change this ID by giving this email address. So when you will click over here, so like this. So accordingly, this PDB has been downloaded onto your book on your Google Colab. So after this, you will have to clean this. The first thing was to download this, and then you will have to clean by giving this command. You will have to clean by giving this command. So this is the command which you will give for the cleaning. Grep -v hoh, and this clean prod clean.pdb. So this is the command which you will give for cleaning. So you can give any name to this, like we have given the name prod. You can change the name as well. Any name you can change here. So okay, we 1AKI. Okay, so this by giving this command, the same command, I am following this tutorial. Okay, I am following this tutorial. That is the Gromacs tutorial. So I have copied this command and pasted over here, and just run this command. Okay, it's good. It's okay. So now we have downloaded the 1AKI.pdb, and then we have cleaned it. After this, I am giving the command bash, and then the source command for the Gromacs, because I am giving the name, the command of the Gromacs as well, the GMX command. Okay, so this is the GMX command. GMX PDB to GMX -f clean, and in this command, the PDB to GMX command will be operated or will be used, and accordingly the force field will be used as well for the topology, etc. So you will have to give this command. Okay, so what was the name? The name of the protein was this. So accordingly, we will have to give this name 1AKI. Okay, so we are going to use this force field Amber 99S. So with this command, like the command is ending over here, that is the output, the input file will be which we have cleaned. That is our input file, 1AKI underscore clean.pdb. That is the file which we have cleaned, and the output file which we want the process, the groove file or the GRO file minus water space. Accordingly, we will have to choose the force field. So we will give the force field with this command as well. Okay, so here till here the command is same, and after this minus ff mean force field, and that is amber 99 sb. So we have given this force field with this command as well. So when we'll click this, okay, it will proceed like that. So it has been processed, and yes, in the end, if you will find the quotation, it means your job has processed successfully. So this was the command which we have given. Yes. Okay, so it has generated the this in the left hand side you can see these are the file which are going to generate. Okay, so next is the topology file has been generated. Next we will have to use the edit conf command uh, for the solvation or for the boxing of this uh, protein. So by using this bash and source command will be used every time when you are going to use the Gromacs. So the same command which we used so far, that let me check the output file. What was the output file over here? That is prot pros.groove. Okay, prot pros. Please be careful about the name of the output file. The name of the output and input file must be same before going to the previous and the further step. If in the previous step the output file name is different from the command which you are going to give, so the result will be, there will be error. Okay, so we have prepared protein process.groove file by the previous command, by this command. uh, what where was the by this command? Yes, this was our output file, and in this step we are going the same file as input file. Okay, so now it will be in the box, and the box size is 1, and that is the cubic. So this command will be again run over here. Okay, it has also run successfully. So this is the command that has been run successfully, and in left hand side you can see the topology file and the prot pros groove and the box file that has been generated. This file, yes, this protein box.groove file that has been generated accordingly, which we have now generated. Okay, so the next step is we'll have to solve it. Is this, we have generated the box, and then we are going to solve it. Okay, so for the solvation, you will have to neutralize it, and you will have to give this command. Okay, so this is the command. We are going to use the same command with the some change the name. Okay, the name which we the file which we have produced in the previous command, that was protbox.groove. So in the next step we will use the same file. Okay, so there are little bit change in the name, otherwise all things are same. You will have, if you don't want to change the name, even you can copy the same command from here, and you can just paste over here. Okay, so if there are some force field used, so you should use the force field accordingly with the command as well. So we will give this command for the solvation. So yes, topology file has been generated, and in the end, yes, there is number of solvent molecules, the volume, the density, the output configuration contain the files, uh, everything that has been 3 atom, and there are some residues. Solvent box contain these atom. 39,252 atoms in 13,084 residues, etc., etc. So these are all the information uh, uh, about this topology file. Okay, the next step is we will have to, what we will have to do, we will have to add, we will have to ionize it. Okay, so for this command will be given here. You will have to give the file that is ion.mdp. Before giving this command, you must have this file. Okay, so this is the file which is written on the, which is available on the tutorial. So you, when you will click over here, so this file will be available over here. So you can download this file and then upload accordingly, or even you can give the address to this file as well. Okay, so in both way you can use this file. So I have given the address, the vget. I have downloaded this file, that is www.mdtutorial.com gmx lysosome file ines.mdp. The same address I have given here by the vget command. Okay, so by typing the vget exclamation vget, and then I have given this path or this address, and when I will run this, so accordingly this ines.mdp file has been saved or downloaded. Okay, so now I can use this command for ionization. Okay, so we must have the input file ines.mdp. So before this you will have to download it, or you can give the address and directly save it onto this Colab. So after giving this, again, as I have already told you, these two commands, bash and source command, must be given. So this command, gmx grompp -f ines.mdp, the total command has been copied and given over here. So when you will run this, okay, so yes, it has processed. Okay, so yes, again the command has been processed successfully. And in the left side, yes, you can check these. ines.tpr file has been generated. Okay, ine.tpr file has been generated. And what was our output file? That was by the end of the command -o ines.tpr file. So this file has been generated after giving this command. So far we are going good. Now we are going to neutralize our protein. So for neutralization, this command will be given. The same command will be copy and pasted, but after giving this command, we will have to select the group 13 for solution. When you will working on the Linux, and you will give this command, and then you will find a table, and you will have to hit 13 to select the solution for embedded ions. So in this command we will give the printf, and the group which we will select, for that we will type the name of the group in quotes, and by the printf command, and then we will paste the command as well. I am making it very simpler for you. You will have to give this command, the simple command. Okay, and when you will give this command, then the system will ask you to choose the group. It will give you the group, and you will have to choose the group accordingly. So you will have to choose the group 13 for solution. So but in this Colab we will give the group along with the command as well by giving the printf command, and then the group which we are going to choose, that is solve sol in quotes, and then give the same command. Okay, so we will run this like this. These are the groups. Okay, so we have choose the group 13. This group has been chosen, 13 group, by giving the printf sol in the start of the command by the printf. Okay, so now we have done so far. We have neutralized our protein. Now we are going to for energy minimization, and for energy minimization we must have this minim.mdp file, and this minim.mdp file will be available here, this. So again, we can download this file, or we can give the address of this file by giving the command vget. So we have given the command vget, and then we have given this address, and when you will give this address, you will have to run this like vget and the address of the minim .mdp file, that is md tutorial.com /gmx lysozyme /file minim.mdp. So while running this, the file minim.mdp will be saved. Okay, it will, yes, it is uploaded. Yes, this is uploaded. The file minim.mdp has been shown on the left hand side. So the file which you will generate or you will download, that will be updated here. Okay, so now we have this minim.mdp. We are going to minimize our protein for n step 50,000, etc. So you can give this command gmx -f minim.mdp, etc, etc, etc. So this command will be copied and by using the source command, and after this command will be given, and then you will have to run the command, and yes, this has been successfully run. Okay, so now this, yes, the file has been updated as well. This was the command, and the output file was em.tpr. Where is em.tpr? Yes, this is em.tpr. So after giving this command, the em.tpr file has been generated and it is shown over here. Okay, so accordingly, when you will follow the step by step, and accordingly file will be added to your directory as well. So after this, you will have to run it, to minimize it. This is a very simple command, that is gmx mdrun -v defnm em. But when you will use the Google Colab, because we are using two CPUs, so this command we have on the pin. You can read about the pin on the Gromacs website when you are using the GPU. So this command, you can give the exact this command as well, but this the command which I am going to give this work more efficiently, that is gmx mdrun ntmpi ntmpi2 ntomp1 minus this is hyphen or minus, you can say whatever you want to say it, defnm am -v pin on, and nbgpu. nbgpu mean you are using GPU for these calculation. Okay, so I am repeating it again and again. you can give this command as well, but we want this minimization efficiently, so therefore we are doing this command. So I will upload these command as well, or I will give the description, these all command in the description of this video as well when I will upload it. Okay, so by running this, it is taking some time. Yes, yes, these are the steps which has been completed, and your protein is minimized. Okay, so you have, yes, the file is updated over here. The EM, TRR and TPR file, log file, EDR file, these has been updated over here. So you have run so far like this. So now you can find out the potential energy. So giving this command, only give this command, uh, you will have to use the, first you will have to use the group 10, then you will have to use the group 0. So while giving this command like this, you will have to prompt the type 10, then 0, 10 for the select potential and 0 for the terminates input. So as I have already told you, these options you should give in the start of the command by the print f, and then in the quote you will give your option, and then this command, the same command which is present on the website, this has been given. Okay, so this is yes, this has successfully run. So this is the energies, last frame was this, these are the details, the bond, the angle, the coulomb forces, etc, etc. There are many things you can figure it out, you can read it about it. So we have find out the energy as well. Okay, so now we are going for equilibration. So for equilibration, first we will use the NVT ensemble, then NPT ensemble. So for NVT, we must have this file for 50,000 steps, for 10 PA, for 100 PS. So you can use this file as well, or you can give this address. So okay, so I will download this file, but I want to change something here. Okay, let me try to do it. I'm just copying it. Okay, I'm just copying it. MDP file. Okay, no, this is MDP. Okay, so I have given this address, that is again mdtutorial.com gmx license file and the file name. Okay, so by the using vget, I have given this address, and the nvt mdp file has been saved. So here, where is that? Okay, it will be uploaded accordingly. Okay, so now we have this nvt mdp file. Again, we are using the command of the Gromacs, so we'll have to use this bash and source command, and the same command which is given here. Okay, for the for the nvt. Yes, this command will be copied and then it will be given over here. So you will just click run. Yes, it has been run successfully. Okay, so yes, you can see this is NVT MDP file. Okay, so NVT TPR, the output file was, what was the output file? The output file, where is the command? Yes, the output file was NVT TPR. So now we have generated NVT TPR. Okay, so this is our output file for the NVT ensemble. So we have given this, and then accordingly we will give this command again, gmx md-run. As I have already told you, we can use the same command, but because we are using the GPUs, so we will a little bit change this command as well, minus v defm minus nb GPU. So this command will be given by using the NVT ensembles. It will take some time because it is of 100 PS. 100 picosecond. It will be equilibrate the system for 100 PS. So I will just check whether how much time it is taking. If it will go too long, then I will download this file MDP and NVT, and I will change the time accordingly. I'm copying it. I'll wait it. If it will take too long, then we'll have to change it. Okay, let me copy this file. Where is the copy? Yes. Okay, I'm pasting it on the desktop. This file. Okay, I'm just waiting for the completion. If it will take too long, so I will update this NVT MDP file accordingly, and I will lessen the time. I will minimize the time so that we can yes, this is NVT. So here you can see that is for 100 PS. If because this is uh, I'm not going to experiment anything. I'm not yes. Okay, it has been completed. Yes, what was the, yes, the performance is, it has completed. Yes, it has completed the performance. You can see the performance over here. This was the command. It has completed. Okay, no, there is no need to change anything. The performance was 71 nanosecond per day. This GPU is giving you 71 nanosecond per day, or 0.3 nanosecond per hour. Okay, so now we will use, we will equilibrate for NPT ensemble, and for NPT ensemble this is the file, and now we will upload it, because I want to tell you how you can upload the file according to your need. If you want to change some file, and you know, this is the NPT equilibration, and here that is 100 PS. I want to make it 10 PS. So accordingly I will change it, and now the name is NPT. NPT. Okay, yes. So the name, so I have changed the NPT file, npt.mdp for 10 picoseconds. So the Yes. Okay, so you can directly download in the same way which we are following, like npt.mdp etc. But I want to show you how you can upload your file. So this is desktop. Where is npt file? Npt. This is npt.mdp file. Okay, what I have done, I have just click this up arrow sign, upload file, and I have choose the directory where the file is present. So my file is present on my desktop, so I have chosen the desktop. And where is this npt? This is npt mdp file which I have uh, yes. So this is, where is npt? Yes, this npt mdp file that has been uploaded. Okay, it is not downloaded by this command we get. I have uploaded it. Okay, so now I will skip this one. I will skip this one because there is no need to download it, because I have already uploaded into this directory. Okay, so now because I have little bit modified this npt file, because for 100 ps it was a long time, so I want to reduce the time as well. So now I have this. I will give this command, the same command which is given on the tutorial, and it will directly use this npt mdp file which I have uploaded over here. Okay, I think if you know little bit about the MD simulation and you have ever used the Gromacs, so you will be following me very easily. Okay, so this is the -f, the input file, that npt mdp, that which I have modified and uploaded accordingly. So when this will be run, okay, so you can see yes, it has this file has been used, and accordingly now I will run it. I will minimize it. npt tpr file has been generated. This is npt. Where is the npt tpr file? Okay, I'm not finding it. This is where I'm not finding it. Okay, no problem. If it won't present, the next command will not work accordingly. So the next command is the same, gmx minus md run minus def nm npt. So I have already told you we will use this ntmp1 etc etc etc. So you can copy, you can give this command. I will upload these command as well, so you can copy these. Okay, so when I will run this, let's see what happened, because I have oh my god, what is this command? Yes. Okay, so now it has processed. We are using we are going to npt ensemble. We are equilibrating npt ensemble as well. So yes, this has been successfully given. Now we are going for the we have equilibrated by npt ensemble, by nvt ensemble. You can find out the this density or equilibration or all these things, but I'm skipping this. You can use this command as well. You can find out the density, the pressure as well, but I am going directly for the md production. For md production, you must have this file, that is md.mdp. So you can give the same address which I have been mentioning and again, you can give the vget command and then this address, the MD and MDP file will be saved accordingly. But uh, this is for the 1 nanosecond. So because it is only the for the sake of the knowledge, so I will minimize the time so that you can find out how you will get the result. Okay, so I have already downloaded the md.mdp file, and I have changed accordingly this one. Okay, so this is my downloaded file which I have already uh, downloaded it. Okay, so this is for zero point zero 0.01 nanosecond or 10 ps. Okay, so I will run the md for 10 picoseconds. So for this I will have to, again, because I'm not downloading the file from here, because it is for the 1 nanosecond, so I and or 1000 picoseconds, so I want to run it only for 10 picosecond for you. Okay, so I will have to upload the file from here. Okay, this mdp file which I have modified, that is present in my download. I will search it, md.mdp in download. This is mdmdp. Okay, so I will upload this file, mdmdp. Yes, this is mdmdp file has been uploaded. This is mdmdp file has been uploaded. So now I will give this command. By uploading this, I will give this command. This is the input file, md.mdp, and then the output file will be md underscore 0 underscore 1.tpr. Okay, so I will give this command as it. Yes, before going to use the Gromacs, you will have to give the source command. Okay, so this is the command which I have given. Now I am going for the running the MD on the GPU. If you are using the CPU, so the Gromacs on window as well, so you can execute the MD run by this command, and if you have the GPU, you can execute by this command. But you can modify the command accordingly, according to your GPUs or pin or these things. So I have because I'm using the NTMPI1 or these command for the better efficiency. So I will run this command, the same command. You can use the same as well. You can use the same command, gmx mdrun minus defnm md underscore 0 underscore 1 minus nb GPU non-bond interaction on GPUs as well. But I am using the little bit change of in this command. I will give this command. It is for the 10 picosecond, and when if you are following the tutorial, it is for the 1000 picosecond or 1 nanosecond. So I have modified the md.mdp file so that I want to make it quickly. Okay, so yes, we are successful. We have completed the simulation so far, and these are the file which we have generated. Okay, so now the next step is to analyze your results. Okay, so next part is analysis. So this is the first command for the correcting the trajectory, or if it is broken, or it is if it jump across the side of the box, so you can correct the trajectory accordingly. And when you will give this command, you will have to first choose the select 1 for protein and select 0 for the system. But as I have already told you, if you want to choose such things, we are using the printf command in quotes the name First we will have to choose the protein. Yes, this is protein, and we are going the name protein, then backward slash, sorry, and then n the system, and then again backward slash, then n, then quote. Okay, the system which you want to choose, you will have to give the name uh, by the print f command, and then you will have to give the same command as well for the correction of your trajectory. So you will run this. When you will run this, you can check over here. This is the command, and the group, first this has been chosen and then this has been chosen. Okay, so the two group has been selected accordingly, which you have given in the command, the protein and the system. First the protein has been chosen, the group 1, and then the system has been chosen. Okay, so both and this is the output file md, because you have centered your trajectory. So this is the file, this is the trajectory file which you have centralized, or you have make in center or corrected it. Okay, so this is accordingly updated over here. So next, if it is not fit, and if there is some problem in the trajectory as well, and you can give this command as well to make it fit as well. Or again, if there are some more problem, you can give the other command. These are command available for the correction in the you can find out any tutorial, you can find out anything on Gromacs. These are already available online, these commands. So now we are going to the most important thing to generate the RMSD, RMSF. These things are important, so we are going to find out the RMSF and RMSD from the trajectory which we have produced or the simulation. Okay, so the source command will be given, and then while you are going for the RMSD, so you will have to choose the backbone. Okay, but I'll recommend you first you choose the select 4 for backbone and select 0 for the system. Okay, so the for the selection, the same command, print f quotes backbone backward slash n system, then backward slash n quotes. This is the option which we are going to choose. In tutorial they have given you should choose 4 backbone for the both groups, but I'll recommend you choose for the first group backbone and the second group system 0. So then this gmx rms command will be given, and in the end minus tu ns flag mean you want this in the nanoseconds, because we have run the MD simulation in picoseconds. So if you want to make the graph in nanoseconds, so you can give this flag minus tu. Okay, so the same command has been given over here, so that will be copied and I will run it, and this minus this rmsd xvg file will be generated. Where is this? Okay, yes, there is an error. What is the error? Okay, look at the error. Error is the file does not exist. Why? Because what was our previous file? What was our previous command? The command which we have, which we corrected it, we corrected the trajectory, and the output was this was the output file, md underscore 0 center dot xtc. But in the tutorial the input file is this. So there is a difference between the input file, therefore there is an error. Okay, so you will have to check, you will have to be very keen by giving the name of the commands. Okay, so I will change the name accordingly. The name was, I think, center. Here will be center. I'm just copying the trajectory which I have corrected. I will find the RMSD by the corrected trajectory. So I will use this name, because this is my output file now. Okay, so I will use this for creating the RMSD graph. Okay, so therefore it is there was an error, because the file was not present. So I will replace that with this one. Okay, now I will try to run it. Yes, my goodness. So yes, it has successfully run. Okay, so where is the output file? The output file was rmsd.xvg. This is rmsd.xvg. You can download this as well if you want to download the file accordingly, because the drawback is the of the Google Colab is, after 12 hours it will automatically reset all the data, so all the things that will be vanished. So you can play smartly while you are doing the simulation on the Colab. So it is recommended, don't go for the more or for the high MD simulation time, like you are going for the 100 nanosecond. So you can choose 15 nanosecond or 14 nanosecond according to your protein, that should be completed into 2 to 3 hour or 5 hour or 6 hours. So if let's suppose you have a small protein and you have given 15 nanosecond and it take 6 hours, so after 6 hour you will find these trajectory files. So save these trajectory files, and then again you can give the command extend by using this Google Colab, and you can extend the same trajectory for more 50 nanosecond. So then it will be collectively 100 nanosecond for two different times. So the problem is if it is reset after 12 hours, so in 6 hour, in two different 6 hour, you can manage these things as well. So you can download the file like this if you want to save the yes, this is this is the file, um, rmsdxvg. So you can this is the file, so you can find the file as well. Okay, I'm just I'll try to give something to show you this. Okay, okay. CD, that is in download. Downloads. Okay, so now Grace RMS. XM Grace RMS. Yes, I want to show you the RMS graph. So yes, don't bother about the results, because that is not for the experimentation. So it was just the tutorial. So this is the RMSD graph. Okay, in this way you can download the file, and you can if you have any tool for make the graph, or you can make the RMSD graph in Excel as well. So I have the grace tool or XM grace. So I have plotted the graph XM grace over like this. So you can use all these commands like this. And if you want to check the RMSF, more analysis, the guy rate, the GMX. Okay, let me do last thing for you. Then we will end this tutorial. Code. Okay, but I have, as I have already told you, you will have to give this source code before this. Okay, this one. Okay, what it, choose protein. I will give this in the start, printf quotes 1, because we are using the option 1. Let's see what happens. Okay, yes, this because there is some problem as well. I have given the I have not given this name. Okay, this was the trajectory which I have corrected. You will have to be very careful about it. So in this way, I think so there is some problem. So in this way, you can find out all these things. I have let me come. I have given this all the commands in this. That was all the commands I have compiled in the file. I will upload the file accordingly. So in this way, you can use the Colab and for your MD simulation. Before going to use the Colab, you must have an account. You should an account on Google Drive, and then you will have to mount the drive by this address, and then you should check your specification, how many CPUs and GPUs you are using, and then accordingly, if you are using the Gromacs, so you must have to install the Gromacs before to going the simulation. So this was all about the Google Colab. Most of you have requested to upload a video on the simulation, specifically by using the Google Colab. So this is about the Google Colab. If you want me to record some other video on the Colab or specifically on the simulation by using the Linux or by using the Gromacs directly into the Linux system, I will upload it accordingly. If you have any question, you can write me, you can send me an email, you can comment, and accordingly I will try to respond. Take care. Bye bye. Allah Hafiz.